All right, so another one to take a look at. This one's a two-parter. Let's see. We've got an unknown piece of metal, weighs 51.5 newtons in air. All right, so when we say weighs, what we're actually dealing with is probably a spring scale, just like we used in class. And so we're holding up an unknown piece of metal, and we read the spring scale, which I'm going to call a normal force. We talked about that before. Technically, we could look at it as a spring force or something like that, but normally when we talk about a scale, just like we did last semester, when I stand on a bathroom scale, it reads the normal force, not the force of gravity on me, but the normal force. Because if I lift my feet up a little bit, then the scale reads less, but that doesn't mean gravity is pulling on me any less. So my normal force in air is equal to 51.5 degrees. They also tell us that the scale reads the following. The normal force in water is equal to 36.3 newtons. And finally, the normal force, the weight in an unknown liquid, I'm just going to call that F and L for liquid, is 41.4 newtons. The first question is, find the density of the metal. Okay, well, if we want to find density, big thing that we're probably looking for, density equals our mass divided by our volume. Now, we're not given much information about this metal. We're given information about what the scales read, which is kind of a tricky approach on this. All right, let's see what we can find out. First off, let's look at the one in air. That was something that was given to us early. I'm going to draw a free body diagram of this just hanging in air. Now, air technically is a fluid, but the buoyant force from air is really, really small, so we're pretty much going to ignore that. So what I'm going to do is this. Here's my free body diagram. I've got the normal force from the scale up and the force of gravity down. Now, if I just have it hanging in air, in fact, let's get an example of this. I have a spring scale. Reads 0 right now. I hang this on there, and I find that it comes up to 1.0 newtons. This is a 100-gram mass. All right? So it's a lot like this. This is in air. And we read the scale, the normal force, and we found that the normal force reads 51.5. 51, this is in air, 51.5 newtons. If I do my sum of forces in the y, for air, I have my normal force in air minus the force of gravity equals my mass times my acceleration in the y. If I have this thing hooked right on here, it says 1 Newton. It's just sitting there. What's my acceleration in the y? Well, 0. It's not accelerating downward, upward, aside from me bumping it a little bit, but it's just sitting there. So my acceleration is actually going to be 0. In fact, in all of these, we're going to find that the acceleration is equal to 0. So when we're in air, we know that the normal force is going to be equal and opposite to the force of gravity, because they're the only two forces acting on it. Ignoring buoyant force from air, but you can solve for it, but it's incredibly, incredibly low. The density of air is about 1.23 kilograms per cubic meter, so it's not going to do much. All right. With this, I know that my normal force in air is going to be equal to the force of gravity, which is mg. Well, we said that the normal force in air was 51.5 newtons, and that's going to be equal to the mass of the object, one of the things we need, times 9.8. Let me see if we've got 9.8 or 9.81. They do not actually specify. It looks like, give me just a moment. We'll use 9.8. That'll be fine. Oh, sorry, meters per second squared. All right, so my mass, well, I'll divide both sides by 9.8. 51.5 divided by 9.8. My mass is going to come up to 5.26 kilograms. I've now got my mass. Now the other thing I need is the volume, how big this thing is. Well, with the information that I've got in air, I don't actually have enough information. We did find the mass. The mass is important because if I want the density, here's the mass. The other thing we need is the volume. Well, let's move on to some other information that we have. Let's go to water. We know a decent amount about water. And this, hopefully, will look a lot like what you have in your notes. I've got the spring scale hanging down to the mass here, which we now know is 5.26 kilograms. And this is underwater. When I do my free body diagram in this case, we've got an extra force that we're looking at. We have the force of gravity. We have the normal force from the scale in water. And we have the buoyant force from water. All right, when I do my sum of forces on this, I'm going to do this a little bit quicker because we've seen it before, but I'm going to have my normal force from water plus, both of these are positive because they're up, my buoyant force from the water minus the force of gravity, and that's going to be equal to 0, my mass times my acceleration in the y. But once again, the mass is just going to be sitting there, right? Well, we know from the information that we've been given, the normal force in water is 36.3. 36.3 newtons plus my buoyant force in water. Well, I'm going to fill in a little bit of what I know. So we know that the buoyant force, first time I've written it in this problem, is equal to the weight of the fluid displaced, which is going to be the density of the fluid, times the volume displaced, times the acceleration due to gravity. Well, density of the fluid, this is water, so that's going to be 1,000 kilogram per cubic meter, times my volume displaced. Well, the whole thing goes underwater. It doesn't float because if it floated, we wouldn't have a normal force at all. The scale wouldn't have to lift it up. So the whole thing is underwater. So this volume displaced is actually the total volume of my object, the other thing that we need, times the acceleration due to gravity, which is 9.8 meters per second squared. And that is going to be minus the mass, which we just found, 5.26 kilograms times 9.8. And all of that will be equal to 0. I apologize that I'm running out of room here. But we have an equation here, and the only thing we don't know is the volume displaced. So I'm going to take on 5.26 times 9.8. That's this one over here, 51. So I've got 36.3 newtons plus 9,800. That's 1,000 times 9.81 times my volume displaced. I'm dropping the units on here, but as long as we put SI in, we get SI out. And this will be minus 51.5 newtons over here, and all that's equal to 0. So I'm going to solve for the volume displaced, 9,800 V. That's my volume displaced. It's going to be equal to, add 51.5 over to the other side and subtract off 36.3. So 51.5 minus 36.3. 15.2 divided by 9,800. My volume is going to be equal to 0.00155 cubic meters. It's a small volume, but as we saw in class, 1 cubic meter is a really big amount of space. So this is normal size. It's actually pretty decent size. It's kind of large, but it's not really, really huge. All right, finishing all this up, density is going to be equal to my mass divided by my volume for that object, because that's what we're asked for. Seems so long ago. They want the density of the metal. That's great. So my mass is going to be 5.26 kilograms divided by my volume, which we just found, 0.00155 cubic meters. That'll give me kilograms per cubic meter. So I'm going to do 5.26 divided by 0.00155. And I end up with the following, 3,394 kilograms per cubic meter. All right, sorry for the cut there, but it looks like I ran out of storage on my camera. So I've been talking to myself for the last couple of, about a minute or so. But I'm going to walk you through. So where we finished up, we had found the density of the object, the metal, And so the final thing that we needed to do for the next part is we have yet to use the normal force in the liquid, which was one other thing that was given to us. So going in here, taking you through, it's going to look a lot like the one that we had just a moment ago in the water, except this time it's an unknown liquid. So I have the spring scale holding the mass down here in the unknown liquid. I do my free body diagram. I have the force from the scale holding it up and the force, the buoyant force from the unknown liquid. And both of those are working together to cancel out the force of gravity. I apologize, these arrows are not drawn to scale. I'm bad about that. But we do know when we add them up, because the thing is just sitting there, it's not floating because we're holding it there, but it's also not accelerating. We have a normal force in the liquid plus the buoyant force from the liquid minus the force of gravity must come up to 0 because there's no acceleration in the y. All right. The normal force that we got was 41.4 newtons, plus my buoyant force is the weight of the fluid displaced, so that's the density of the unknown liquid, times the volume displaced. We know that this went all the way beneath the liquid, so this is the volume that is displaced, times 9.8, our g, so take a look at what we did in the water. And then finally, minus mg, we know the mass is 5.26, and that the acceleration due to gravity is 9.8. All of that needs to total up to 0. I've done some math here, but this term, I moved the others over, and I end up with the density of the liquid times the volume times 9.8 equals 10.1. And then solving for rho, I divide both sides by these values, and I end up with rho being equal to 664.9. To 4 significant figures, I would normally call this 665 kilograms per cubic meter. Now, I got lazy and left the units out partway through that, and I was running out of space. But remember, go through and check, make certain the units work out, but the thing to remember is if we put SI in, we will get SI back out. That's the point of having an SI system. So there we go.